Chapter 3, Describing Data Using Numerical Measures. In this video, we'll learn how to compute a z-score as well as the coefficient of variation, and talk about how to use the empirical rule in Tchebysheff's theorem. Recall in the previous videos, we learned about the mean and standard deviation, two commonly used measures in business and in this course. So a mean is a measure of center and location, whereas the standard deviation was a measure of variation. Together, this allows us to calculate something called the coefficient of variation. This is the ratio of the standard deviation to the mean and is always expressed as a percentage. It essentially shows us the variation relative to the mean and can be used to compare two or more sets of data measured in different units. So imagine if I wanted to compare the variation or the test scores of a math class and a Spanish class, which will have different questions, different exams, and different students. We can use this formula and compare the variation of each group. So here we have our formulas down below, the population coefficient of variation and the sample coefficient of variation. And you'll notice that the formulas are very similar, except that it uses different Greek letters depending on what we're talking about. So here under the population CV, we see sigma, which stands for the standard deviation of the population, and we see mu down below, which is our population mean. So we'll take the standard deviation of the population divided by the mean of the population and then multiply by 100%. Similarly, for our sample coefficient of variation, we have lowercase s, which is the sample standard deviation, and we have x bar, which is the mean of the sample, or the sample mean. And then we'll divide the two and multiply by 100%. Let's look at an example. Here, problem 50 from your textbook. You were given the following parameters for two populations. So remember, I mentioned before, P's go together, parameters, populations. In part A, we're going to go ahead and compute the coefficient of variation for each, and we're just going to plug in my numbers into the formula. So first we take our standard deviation of 50 and divide by our population mean of 700. Then we'll multiply by 100%, which will give us 0.07, which we then have to convert into a percentage because coefficients of variation are expressed in percentages. So the coefficient of variation for population 1 is 7%. We'll do the same thing again for population 2, but using the numbers in our table for that population. We'll first take the standard deviation of 5,000 and divide it by our population mean of 29,000, and then multiply by 100%. This gives us 0.17 or 17%. Now in part B, it asks which population is more variable relative to the size of the population mean. So what we want to do is compare our coefficients of variation of our two populations, and whichever one is greater, that's the one that has more variation. So we know that population 2 has greater variation at 17% than population 1, which is only 7%. And if we imagine our bell-shaped curve, we know that population 1 will have a tighter, skinnier curve where the data is closer together when compared to population 2, which will be wider and more spread out at 17%. The empirical rule is another useful rule to understand our data when our frequency distribution is bell-shaped. So recall in chapter 2 when we were calculating frequency distributions, some of them were shaped symmetrically, like a bell. So according to the empirical rule, here is my population mean in the center. And if I go up one standard deviation and down one standard deviation, I know that between these 2 points, 68% of my data values will fall here in the middle. If I go up 2 standard deviations and down 2 standard deviations from the mean, then I know that 95% of all my data values in a data set will fall somewhere in between here. And if I go further out to 3 standard deviations from the mean, meaning I go up 3 standard deviations and down 3 standard deviations, all my values within my data set are virtually in here. If you have numbers that are greater than 3 standard deviations away from the mean, they're generally considered outliers. They're extremely small or extremely large as it relates to our population mean. So let's look at an example of how we could use this to estimate our data. So imagine in San Diego that we've collected data on Uber rides, and it was found that the population mean for Uber rides is around 15.1 miles per ride, and that the standard deviation is 3.1 miles. So we'll go ahead and plug in our mean and standard deviation. Here, my mean of 15.1 goes here, plus or minus, and we're looking at one standard deviation away. So we'll take my 1 and we'll multiply it by my standard deviation of 3.1. We know that equals 3.1. So then what I'll do is I'll take 15.1 minus 3.1, that'll give me my lower limit, and 15.1 plus 3.1, which will give me my upper limit. So that means I know that within one standard deviation of the mean, 68% of Uber rides are somewhere between 12 and 18.2 miles in distance. Next, let's do two standard deviations. So I'll plug in my numbers. Here's my mean, plus or minus, and I'm looking at two standard deviations from the mean. So 2 times 3.1, or 6.2, and then I'll subtract 15.1 minus 6.2, will give me my lower end, and if I do 15.1 plus 6.2, it'll give me my upper end. So I know that 95% of our car rides are somewhere between 8.9 miles and 21.3 miles. Tchebysheff's theorem is another useful rule of thumb similar to the empirical rule. Whereas the empirical rule is used for bell-shaped distributions, Tchebysheff's theorem is for non-bell-shaped distributions. So it's much more conservative, and we can see here in our example, this is not symmetrical, it's not bell-shaped, it's skewed. And what it can tell us is that at least 75% of our data values are going to be within 2 standard deviations of the mean. Tchebysheff's theorem also tells us that at least 89% of all of our data values will fall within 3 standard deviations of the mean. Again, because we're being conservative, we don't know anything about the data as it relates to 1 standard deviation of the mean. Hence, we have at least 0. So can't really do much with it. But we can use Tchebysheff's theorem to estimate the percentage of data values within 2 or 3 standard deviations of the mean. Note that it says at least because it could be greater than, depending on how the curve actually looks, but this is a conservative estimate of at least 75 or 89%. So that's all Tchebysheff's theorem is. It just allows us to estimate where our values might fall when our curve is not bell-shaped. Let's go ahead and work with standardized data values. And so recall in my example earlier when I wanted to compare test scores of math students and Spanish students, standardizing data values allows us to compare different things, different measures, on a consistent scale or a standardized scale. And so this will be called z-value or z-scores. So here's our z-score formula for population and sample. And again, you'll notice they're similarly structured, they just have different Greek letters so you know what you're working with. So here, our x in both formulas is the data value we want to convert into a z-score. And then here is our mu, or the population mean, and that gets subtracted from our data value. Similarly, if you're doing a sample z-score, this is our x bar, or sample mean, and that gets subtracted from our x value. In both formulas, you'll divide it by the standard deviation. So let's go ahead and see an example. Imagine that IQ scores have a distribution thought to be bell-shaped, where the mean is 100 and the standard deviation is 15. So if I have a person with an IQ score of 121, we want to know what their standardized IQ is. So here we'll have our population mean of 100 and our standard deviation of 15, and plug it into our formula. So my x, my person with an IQ of 121, subtracts 100, which is the average score, and then we divide by our standard deviation of 15. That gives us a z-value or z-score of 1.4 for the person with 121 IQ. In other words, a person with an IQ of 121 is 1.4 standard deviations higher or to the right of the population mean IQ. So if I imagine my curve, I'm going to be on the right side. Let's go ahead and practice using problem 53. Here you'll notice we're talking about samples, but the process is the same. I've got my formula for the sample z-score right here. So we'll take the x value that we're interested in converting, subtract our sample mean, and divide by our sample standard deviation. So the number I want to convert is 800, so I'll take 800 minus 1,000, and then divide by my standard deviation of 250 to get me a z-score of negative 0.8. The negative tells me I'm on the left side of my curve, and so we've got negative 0.8 standard deviations away from our mean. Let's do the same thing for part B. We'll take my x value I want to convert, 1200 minus 1,000, then I'll divide it by my standard deviation of 250, and that gives me a z-score of 0.8. This is on the right side of our curve. We are 0.8 standard deviations to the right of my sample mean. Let's do one more in part C. If my x value I want to convert to a z-score is 1,000, I'll take 1,000 minus my sample mean of 1,000, divide by my standard deviation of 250, and I have a z-score of 0, because essentially my value I'm interested in finding is my mean, because 1,000 equals 1,000. So I'm right in the middle of my distribution. So that gives us a z-score of 0. If you have any questions, just let me know.